All right. So, again, just as I stated, just for the video, I'm going to restate it. There are about 5 ways in this unit that I'm going to teach you on how to find the enthalpy of a reaction, the delta H. The first way is to use that molar enthalpy. Delta H equals N delta HX, right? Delta H equals N delta HX. So we know how to use that one. That was the easiest form. Then we did calorimetry, where we did Q, negative Q equals delta H, right? And then we put together with that negative MC delta T equals N delta HX. So that's the second way. That's the first way, that's the second way. And we used that one in our lab just recently. You'll be using that again, right? The third way is using Hess's law, and I don't have any way to write down Hess's law except the fact that if you've got a bunch of reactions, you can flip them around and multiply them by a factor and get the, overall reaction. So that's the third way. The way I'm going to teach you today is obviously bond energies, and that's looking at the energy of an individual bond. Chemists are able to, through various experiments and using Hess's law and all kinds of different mathematics, to come up with an energy for a particular bond, that a mole of those bonds would, on average, use or produce that much energy when you make or break that particular bond. So today we're going to look at individual bonds and the energies involved with them. And then the last method, which is tomorrow, is using something called heats of formation, and that's a special type of reaction that I will, review with you again tomorrow. Again, I'm just kind of looking at the clock. Okay, so next here, let's talk about what happens during a chemical reaction. And so during a chemical reaction, bonds need to be broken as the reactants kind of fall apart or blow apart during a chemical reaction. A chemical reaction is a violent thing, really. We see the energy given off when, even in this reaction where we're trying to break apart the water molecules to produce hydrogen and oxygen. Like, you've got to put electricity into that. That's that reaction you saw in grade 9 using what we call the Huffman apparatus, right? We put electricity in there, it zaps the water, and it produces some hydrogen and oxygen. That's a violent reaction. We're tearing bonds apart using electricity. We're allowing other bonds to form. So we have to tear apart the molecules. And when you tear apart a molecule, you put energy in. The breaking of a chemical bond is an endothermic process. If we were to look at just, say, the delta H for breaking a bond, it would be positive. We have to put energy in to pull apart 2 atoms in a molecule. You can think of it like pulling apart 2 magnets. Magnets are attached to each other by a bond. Anything that holds anything together, it's a bond. It's magnetic force that holds it together, but it's a bond. And if I want to break this bond, I've got to put some energy into it. Yes. Whew. That's a lot of work. And it actually is work, because work equals force times distance. You want to see me break it again? Yeah. I hope I don't have to do that too many times. It might break a sweat. No? Nothing? This is for the video. I want to be funny at the same time. No? Here, I've got another one. See? You want to see me break another bond? I'm going to have to do work, right? All you physics people, we know work equals force times distance. I did that 3 times. You know how much work that is? So, if you've got parents that say teachers never do any work, tell them about today. No? Nothing? Yeah, thank you. Thank you very much. Okay, so when you break bonds, it takes energy to break those bonds. It's endothermic. As products are being formed, the atoms are rearranging into product molecules. Something's beeping. That's probably my device. Anyway, bonds are being reformed. Things are sticking together, and energy is being released as bonds are being formed. The same can be said about our magnets. If magnets are brought together, that collision, that kinetic energy releases some energy. In this case, it was sound, right? There's some energy being released. In a chemical scenario, that crashing of the atoms together to form the bond causes them to vibrate and shake, and that's heat energy, so it gives its heat off, okay? So when bonds are formed, heat is given off. So breaking bonds is endothermic, positive. Forming bonds is exothermic, negative. So what then is a bond energy? The amount of energy required to break 1 mole of bonds between 2 particular atoms. So we're doing an analysis on an atom by atom basis. Each bond we need to total up. Like I said, these values have been determined through experiment and then ultimately some mathematics using Hess's law type calculations. And in the end, chemists can deduce what the value in kilojoules per mole of a mole of those bonds being broken or formed would produce. On our reference tables, we're looking at, and I don't remember which one it's called, I think it's on the one that has KSPs and then KAs, and it also has bond energies. So I'm looking at this table right here, and so it's got the KSPs, right? And I think on the back side, sorry, that's KAs and KBs, KSPs and bond energies, okay? That's the one you're going to use when you do a test, okay? I have it up on the slide here, and I'm going to advance this slide in a moment. We're going to be able to take a look at these values. So it's going to look just like that. And if you've got that table, you can see that there's all kinds of numbers on them, and it's just kilojoules per mole. You'll notice also that the numbers don't have any signs to them, because we put a positive if we're breaking the bonds, and we put a negative if we're making the bond. And then we total it all up in the end. It's really just an accounting of how many bonds are broken and how many bonds are formed in the end. So this is just accounting, really, what we're doing here. I'm trying to be patient, but I'm not. Good to go? Or are you just feeling the pressure? Bradley's feeling my pressure. Okay, so there is an image that is exactly like the table that you can you have that you can use, and you can see here we've got some single bonds. The hydrogen single bond 432, hydrogen fluorine 565. So that's pretty strong bonds. Here we've got some double bonds and triple bonds. Carbon double bond carbon 618, carbon triple bond 839. You'll notice the multiple bonds are even stronger than the single bonds. We're going to learn why that is when we talk about bonding and how the atoms' orbits overlap. So multiple bonds tend to be stronger. Notice here we've got carbon-oxygen bond, 745, but also note in carbon dioxide, that carbon-oxygen double bond is actually even stronger. So there's something special about the carbon dioxide molecule which makes that bond a little bit stronger, okay? So, again, my table isn't very distributed very well. There's the values there. There's the values for that column. This one's very wide for some reason, and there's the values for our multiple bonds, okay? All right? Again, notice there's no signs on them, and that's because when we break the bonds, it'll be endothermic, and we will have positive values, and when we make the bonds, it'll be exothermic, and we will have negative values. Any questions or concerns? All right, let's do some math that deals with these. So if we want the total delta H for the entire reaction, then we're going to add up all of the energies of the bonds that are broken, in other words, the reactant bonds, And because we're breaking apart the reactant bonds, it's endothermic. And so because it is endo, this is positive. I don't have a positive written in front of it, but it's positive because it's endothermic. Sorry, yeah, endothermic, yeah. We're breaking the bonds. It takes energy. And when we put the bonds together, it gives energy off, and therefore the negative sign right there makes this exo, and therefore it's negative, right? We put a negative there to represent the energy we get back out. If we have to put more energy in to break the bonds than we get back out, then the overall reaction will be positive, and the overall reaction will be endothermic. And if we get more energy out by forming the bond than we invested in putting in, then we'll have a negative value, and it'll be an exothermic chemical reaction. We'll get our energy out. Are we aware of this symbol, the sigma, to use as a sum? Have you seen that in math before? Some you have, some you haven't. This is a Greek capital letter called sigma, and it essentially means the sum of all of the bonds of the reactants and the sum of all of the bonds of the products. What math do you learn that in? Data management. So if you haven't taken data management yet, or you're not very far in, you might not have seen that. This means to total it up, the sum. Okay? Let's do some examples. Now, in order to do bond energy problems, you need to know the basic Lewis structures. Now, I haven't officially reviewed Lewis structures with you. So there are a few Lewis structures that I'm going to expect you to know for the test. And then if it involves a complex molecule, I will give you the Lewis structure. All right? Hydrogen and oxygen and water, I expect you to know how to draw the Lewis structures. So these you'll have to memorize. Now, the first thing we have to do is balance the chemical equation, because we need to know all of the bonds that are being broken. So I think to balance this, I'm going to need a 2 and a 2. That looking good? Don't let me mess it up. Again, I'm clock watching and I'm recording, which means many mistakes by Mr. Sanders. So don't let me, if you see something, stop me right away. Okay? All right. So we need to kind of draw it out in order for us to see it. I've got H single bond H. Now, you don't have to draw out 2 of them. I'm not that concerned. But in the end, I'm going to have 2 of these H single bond H bonds, right? Oxygen, O double bond O. I'm not worried about the lone electrons. We're not worried about that. We're just worried about the bonds in this case. And water is O, H, H. And if you didn't put a bend in it, it's not a big deal. Okay? So, delta H. Now, I could create some fancy equation, but I don't think it does a service to do this here. What I need to find is the energy for the H single bond H, and I need to multiply it by 2, because there's 2 of those. So in the textbook, it's going to have N of the H single bond H, and they're going to use subscripts and all this big kind of fancy equation, but that's overkill. If I look at my chart, and I'm not going to flip back to the previous slide, H single bond H is 432, okay? So I'm going to break 2 of those. 2 times 432. I've located that on here, and I'm just determining how many of those bonds I have. Still looking at the reactants. I've got one of the O double bond O, and if you've got this sheet nearby and you can find the numbers for me, it'll make my life a little easier. Abby, did you find O double bond O? 495. Now, I want to total these all up, so I'm going to put some big brackets around it to represent the reactants. Now I'm going to do the same for the products, except it's going to be subtracted away. HO, there's two of them in each water molecule, and I have two water molecules. So how many HO bonds are being formed? 4, okay? 4, and do we have H single bond O? 467. 467. That is all of the products. Now we do the calculation. Yep.
Can I get Bradley Hall to the office to sign out, please?
Yep.
Thank you.
Take that with you. Okay. That'll be up online when I get that taken care of. It actually might not be today because I got to go to the hockey game and all that other stuff. We'll see. I would suggest you do this as two separate calculations, as not to mess up the math. Could somebody tell me what that first bracket value is and what that second bracket value is? Please do them separately. Why am I telling you to do them separately? Because I screwed that up in university about 1,000,000 times. All right, maybe not 1,000,000 times, but my mistake was always made when I tried to do that in a hurry and in one shot. It never saved me time because I always got a bracket wrong or something crazy. What do we have in the first one? 59. That's the energy needed to break all those bonds. What do we have being spit out? 1,868, which means we're getting energy out, right, in total. So what do we have in terms of the delta H? 509 minus 509 kilojoules per mole. All right? Does that make sense? That is a very simple technique. It's a very simple technique. All right. Let's do one more example, and then I'll leave you to work. No good? We okay? Did I move too quickly?
No.
We're okay with that? Okay. Always balance your equation. Again, I'm in a little bit of a hurry, so I will help you balance this equation. 1 carbon, 1 carbon dioxide, 4 hydrogens means 2 waters. I've got an O2 there, and those 2 O's will make a second O2, right? So I should have 2 O2s. Again, a simple Lewis diagram of each of them are going to be needed. I would hope you could do CH4, but if I give you a large hydrocarbon that has lots of carbons and hydrogens, I would draw it for you, okay? But CH4 is just C, H, 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 H. We've already encountered our O2, which is one I'm going to expect you to know. I'm also going to expect you to know CO2. So that's the other one I want you to memorize. And water we've already seen. Again, we're just adding up our bonds broken, subtracting away the bonds formed. What am I going to put for our first thing here? How many bonds am I dealing with? Yep, 4 CH bonds. Again, keep an eye on the coefficient. In this case, it's only 1, so it's 1 times 4. And did anybody check a CH bond? 413. Again, watch the coefficient. I've had teachers, or I've seen textbooks where they draw out each molecule. 2 O2s, right, and 2 H2Os. But if you keep an eye on your coefficients, you should be fine. So 2 of those bonds, and we've used it already. What was that number again? 495. That's all my reactants. So again, I'm going to gather that up as one number. I have 1 CO2, which means I've got 2 of those bonds. 2. Now, I do want you to be aware, we're talking about CO2. So what bond energy are you going to use? What's the value for O2? Sorry, for a CO bond in a CO2? 799. That's that one that's at the bottom. That's that special case one. Be aware of that. 799. 799. And there's only 1, so that's good. And I'm going to have 4 OH bonds. And you guys, a lot of you guys are doing the math already, so you're way ahead of me. OH. Right there. 467. 467. Close that bracket up. Again, my personal view is to do them separately. You got numbers there, Taylor? What do you need there, Taylor? Okay. All right. What do we have for the first? I want the bonds being broken energy. I want them separate. 2,642 kilojoules to break those bonds. And how much energy is given off? 3,466. Make sure we're checking these. We got supporters on these numbers. Looking good. Far more energy given off in forming the product than in the reactant. So again, we're going to have a negative. And what do we got? Negative 824. Negative 824 kilojoules per mole. And this is really kind of per mole of CH4 because there's a 1 in front of it there, right? Okay, excellent. All right, so bond energies is a straightforward way of doing that. There's the practice problems right there. Don't worry about the chapter review stuff quite yet. This actually came at the end of the unit when I've taught it there in the past. I will be talking more about the chapter review problems when we get heading towards a unit test, which is at the end of next week. All right, so I'll talk more about that. Just worry about the practice problems, okay? So at this point, I'm going to stop my recording.